Hello, my name is Sergio Laut. I'm a PhD student at Barcelona Supercomputing Center, and this talk's title is Cache-aware sparse patterns for the factorized sparse approximate inverse preconditioner. So let's begin with our motivations and goals. In many simulation codes, we're required to solve linear systems with the form AX equal B, where A is a known matrix, X is an unknown vector, and B is a known right-hand side vector. These problems are usually solved in systems whose memory is becoming complex, that they have complex memory hierarchies, and it is critical and it is crucial to properly manage those memory resources and memory hierarchies in order to achieve a good performance. Now, some of the methods that are used to solve these problems are iterative, and some of them require a preconditioning step that allows to improve their convergence properties. Now, what we want to do is to develop a preconditioner that does not only consider numerical criteria, such as most state-of-the-art preconditioners, but that does also consider some computing aspects related with memory management in order to improve the preconditioner efficiency. So this is the outline I'm going to follow. First, I'm going to talk a little bit about the conjugate gradient and the factorized sparse approximate inverse. Those are the 2 points directly related to the work background. After, I'm going to demonstrate our cache-aware pattern extension and filtering ideas. And after, I'm going to show some of the results in the infrastructure and dataset that we have obtained. Finally, I'm going to draw some conclusions and talk about our future work. So let's move to the conjugate gradient. The conjugate gradient is an iterative solver for linear systems with the form such as the one we saw before, AX equal B. It is used in symmetric and positive definite matrices. We can see the algorithm of the conjugate gradient to the right. And it has several inputs, A, the system matrix, B, which is the right-hand side. We need an initial guess for X, which for us, we will always consider it to be 0, and some stopping criteria, which is the maximum amount of iterations and the convergence tolerance. As you can see, it only requires some linear algebra operations. Those are the linear combinations of vectors, which is also referred as AXPy, the dot product, and the sparse matrix vector product. This algorithm also has a preconditioned version in which the preconditioning step, which is added during the iterative steps, improves its convergence properties. It has the same inputs as the simple conjugate gradient, and it requires a preconditioner. It might be a block Jacobi, a multi-grid technique, an incomplete LU. But the one that we will use as preconditioners is of the type approximate inverse, which we will apply in the solver stage in its factorized form as two SPMB products. We can see that as the form G times G transposed. And these two SPMB products approximate the inverse of A. So let's get into detail in the F side. Well, any sparse approximate inverse methods are based on the idea that the inverse of a sparse matrix is dense but contains some small entries that can be neglected, that they have a very small numerical value. And in the case of F psi, what we do is to approximate to evaluate G, which is an approximation to the inverse of the Cholesky factor of L, the Cholesky factor L of A, and we compute it on a fixed sparse pattern S, which is a lower triangular pattern. We compute the values of G using the following minimization problem. In this equation, we minimize the Frobenius norm, which is the square root of the sum of the absolute squares of the matrix elements. And the interesting idea here is that this equation can be solved independently for each row without explicitly evaluating L. That means that this method is highly parallelizable and thus highly interesting. Now, we have one degree of freedom here, which is the selection of S, of the pattern that we will compute G on. Now G is only computed once during the preprocessing stage, and we apply it in its original form G and G transposed once in each iteration of the solver stage of the conjugate gradient. Now there's different methods to find the lower triangular pattern to compute the values of G. There's static methods and dynamic methods. For the static methods, we select the pattern before computing the approximation values, and we keep it unvaried throughout the computation. Take a look, for example, at figure 1, in which we have a sample matrix A. One case for a static method could be to just use the lower triangular pattern of said matrix. Now there's also dynamic methods, which are the adaptive procedures that start from an initial guess, say for example the diagonal pattern, and they construct a new pattern subject to some criteria. They grow this diagonal pattern and obtain a new one. They're usually computationally costlier, but they are also slightly better. So, as I said, Fpsi is applied through two SPMB operations in each iteration of the solving stage. Now, suppose that both G and G transposed are stored in CSR format. That is, each matrix is stored in three vectors, the first one containing the values of the matrix, the second one storing the column indices, and the third one containing pointers to the values and column indices vectors to the beginning of each row. Now, in an SPMB operation, the accesses to the values and columns of the matrix show a simple straight one pattern. That means that they are easy to predict accesses, and the prefetcher here can predict the data that we are going to be used. However, the accesses to the multiplying vector are matrix dependent. They are hard to predict, as they depend on the values of the column indices. Take a look, for example, at this row. In this row, we have 5 entries, 5 different column indices, which in the CSR format they are stored one after the other. Here's the straight one pattern, but we have to access different positions in the multiplying vector, which are far one from another. Plus, every time we load one of the elements of the multiplying vector, we are not only loading that one, but a bunch of elements in the form of a cache line. If the matrix is sparse, then some of the loaded cache line components are not going to be used. So what's the idea here? What do we don't want to do? We want to define the pattern. We want to extend a pattern in order to take advantage of all the loaded cache line components. So here's where our cache-aware pattern extension and filtering ideas come. So we have our algorithm for pattern extension on the right. This algorithm can be applied to any given initial pattern. And the idea is that we want to add entries to the pattern that do not increase cache misses on the multiplying vector axis. That, if we recall, those are the ones difficult to predict, and thus the ones that have a higher computational cost. The only inputs for this algorithm are an initial pattern that we want to extend, the multiplying vector, as we need to know the relative positions in memory of the entries in the multiplying vector in order to perform the cache-aware pattern extension, and the cache line size, which is an architectural input. So consider the previously seen row. We have 5 different cache lines from the multiplying vector that are loaded, and from all those different cache lines we are only using 5 elements, even though that we are loading 40 entries. So what we want to do is to try to use as many of those 40 entries as we can. The resulting pattern, once applying our algorithm, would be something like this. The pattern would be formed by all the non-white positions, and we would evaluate G using the Frobenius minimization problem that we saw, using this pattern. As you can see on the right, we have the CSR expression of the row that we saw before, and now it contains many more elements. However, we have one problem here, and it is that if some of the added entries may not contribute to the numerical quality of the inverse approximation, this means that even though they will have some computational, a low computational cost, maybe they will not help to reduce the iterations to convergence of the solving stage of the conjugate gradient. In order to solve this problem, what we have to do is to filter out some of the added entries. The resulting pattern could be something like this. The pattern would be formed by the black and the red positions. Now, once we filter out the entries, we do not have the best approximation to the inverse in the resulting pattern. That means that the Frobenius minimization problem is not valid anymore here, and thus we have to recompute G in order to have the best numerical properties for the preconditioner in this pattern. Now this looks like we have to compute twice the approximation to the inverse, but since the first one in the extended pattern we only need it in order to find the different orders of magnitude of the extended entries, we can make a rough approximation using, for example, floats, and using and solving each of the rows with an approximation that leads us to these orders of magnitude differences. Also, once we extend the pattern, what we are obtaining is performing a spatial locality optimization in the G product and temporal locality optimization in the G transposed. So we can perform the same optimization for the G transposed, and we will obtain optimizations for the two products. Now it is quite important to note that the two optimizations must be performed in two separate steps, because otherwise it would not be sure that the extended entries are cache friendly. So let's move to the infrastructure and dataset. We have used three different architectures, Skylake, Power9 and A64FX, in order to prove that our method can be applied to any of them. In Skylake and Power9 we have 64-byte L1 cache lines, and in A64FX we have a 256-byte L1 cache lines. This is quite important because if we recall, our method depends on the cache line size. Now our implementation has been performed in C. The code has not been changed in the three different architectures, and it has been compiled with GCC. We have used a dataset with 72 test matrices from the suite Sparse collection, ranging from 48K to 4.8 million non-zero entries, and they come from very different fields and have quite a range of densities and variety of sparse patterns. So let's move to the results. Since we perform an optimization that mainly affects to the SPMB operations, we will first validate the improvements that our pattern extensions bring to the SPMB operation, and we will do that by analyzing the effects on cache misses and the effects on flops of the pattern extension. And after we are going to see some of the time improvements that we have obtained on different architectures using the solver with our improved preconditioner. In all the cases, what we are going to perform is an optimization of both both G and G transposed products. So first let's see the effects on cache misses. On the right we see 3 histograms. The blue columns correspond to the baseline F psi. The orange columns correspond to the pattern extension that we have proposed, our method. And in green what we see is a pattern extension, but that does not consider cache awareness. What we are seeing is the amount of L1 cache misses on the multiplying vector axes per non-zero entry of the lower triangular pattern in the SPMB operation. Now, what we see here is that cache aware pattern extensions reduce in an important way the cache misses per non-zero entry, while on the other hand, by randomly extending a pattern, leads to an important increase in cache misses due to the bad memory usage. Here we can see that cache aware pattern extensions bring an optimization into the SPMB operation. Now, if we take a look at at flops, we have a histogram on the right with the same legend as before. In this case, what we see is that if we perform a cache-friendly pattern extension, we will be increasing flops in the SPMB operations. And on the other hand, if we perform a random extension, that is without taking into account the cache friendliness of the extension, we will have a considerable and important decrease in flops due to the bad memory usage. So here now we will see some of the results for the different architectures. First, we see Skylake. For Skylake, what we have done here is to show in the table different values of average iterations, average time, highest improvement, and highest time degradation for all the matrices in the data set. And what we see here is that for different filtering values and for the best filter for all the matrices in the data set, what we obtain is that an average iteration decrease of 16.60% and a 15.02% in time decrease. As we can see here, the best filter value, the best general filter value is 0.01. Now, if we look at the general results, we can see here that many of the matrices show time decreases of more than 20%. In the case of Power 9, we achieve similar results. In the case of the average iteration decrease, we have a 15.15% and an average time decrease of 12.94%. As before, we have quite important time decreases. And in the case of A64FX, we now have larger values, mainly to the larger cache lines. We have an average iteration decrease of 24.91% and an average time decrease of 22.85. We can see here that there's quite a lot of matrices that have more than 30% of time to solution improvement using the conjugate gradient. So we will now show some conclusions and future work. We have a pattern extension method that provides significant conjugate gradient iteration reductions with a low overhead. We can apply this method to any sparse pattern evaluation strategy, and we have some a filtering out strategy that allows us to optimize the cache friendly extension. We have proof that our method works, showing some time improvements between 12.94 and 22.85% in different architectures without having to modify any of the code. Now, as future work, we are working on the MPI implementation, and we are further developing our method for GPUs. So that's all. Thank you very much. I will now answer any questions.